All right, so we are on lesson 7.1. So the start of unit 7. And in this unit, we're going to talk about exponents and logarithms. So we have talked about exponents a little bit in unit 6. And what I want to first start with is how to graph exponential functions. And exponential functions have tons of applications in real life. They help model interest. So that means with loans, with investments, with savings accounts, with credit cards, they can model all those things. They can model the spread of a disease. We can use exponential models to model the depreciation of a car. So we're going to talk about some of those applications. And mostly what I'm going to focus on is compound interest, because that's, I think, the most relevant to your life eventually. So before we do that, we have to understand what the parent function for exponential growth functions and decay functions looks like. So an exponential growth function looks like f of x equals b to the x power, where the b value, I'm going to call that the growth factor, is greater than 1, okay? So the base is b. That's your growth factor. So this would be an example of a function that is doubling, okay? Or a function that is tripling, or a function that is increasing by 1%. But these functions increase by multiplication, repeated multiplication. And these graphs, they rise from left to right. And it's just noticing the domain of these growth functions is all real numbers, and the range is values greater than 0. Now, exponential decay is when the growth factor, or the factor we're multiplying by, is between 0 and 1, meaning this could be something that is getting cut in half, or something that is decreasing by 1%. But it's that same repeated multiplication, but it's a multiplication that reduces our y values as we go from left to right on our graph. So the range of these functions, these decay functions, is still 0. But the main difference is that growth functions have a growth factor, decay functions have a decay factor. So we're going to talk about telling the difference and then graphing these functions in example 1. So the main thing I want you to do with exponential functions is realize whether they're growth or decay. That's the first thing. And then be able to graph mostly basic ones. So in this first function, we look at this function. It's y equals 2 to the x power. So that means our factor, or our rate of change here, means 2. Okay, 2 is our base. So this represents an exponential growth function. And we're going to illustrate that in the table. So I'm just going to choose numbers or inputs, -2, -1, 0, 1, 2, 3. And it's doing 2 to the -2 power, which is 1/4. 2 to the -1 is 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So this is how our function will look if we graph it. And we could graph more points if we wanted, but this just gives us a general idea of what this graph looks like. And the thing I want you to notice in this table is that as we go from left to right, as we increase our x values by 1, we are doubling our y values. That's where this 2 comes in. It's our growth rate. This function is doubling, okay? So it's doubling. So we're going to connect our points with a smoothish curve, best we can. I'm not going for perfection. And then I want you to draw this as we go to the left. I'm not going to do a good job, but we want it to show that it's approaching 0 without ever actually reaching 0. And we're going to illustrate that better in the second function, where its base is 1/2. So for this function, I'm going to choose -3, -2, -1, 0, 1, 2. You can choose any numbers you want that are on, any x values that are on the graph, but I usually choose small numbers close to 0 because they seem to be easier to evaluate. So in this too, if you're wondering where I'm getting the outputs, it's just me plugging in 1/2 to the -3rd power. So I kind of go through that fast, but you can do this by just simply doing 1/2 to the -3rd power to get your output. So in this function, my output's going to be 8, 4, and if you notice the pattern, we are dividing by 2. or multiplying by a half, which is the same thing. So 2 to 1, and then 1/2, 1/4. So it's kind of like our other function, sort of in reverse. So if we look at this, -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, and then 2, 1/4. So the thing we notice here is it's almost like our function looks like it's sort of mirrored, but it's understanding that this function, and I'm doing my best to show that it's getting close to 0 without ever actually reaching 0, but we are cutting our function in half. So the thing I forgot to say here from the beginning is that this function is decay because our base is between 0 and 1. Our decay rate is a half. In part A, we had a growth rate, and that was 2. So this part A, we were doubling our values. Part B, we were cutting our values in half. So if we keep cutting something in half, that that y value will never be 0, never be completely 0. It will get super, super close to 0. It will get so close to 0 that we really can't tell that it's not 0. But we just got to say half of something isn't 0. Half of something is still something. So decay values are decreasing, growth values are increasing. So the next part of this is to apply this to exponential models, meaning exponential functions that model real-life situations. So something's increased by a fixed percent. So we usually work with percents with growth and decay in real life. After a certain amount of years, 90% of the applications you're going to deal with in science a lot of times is going to be over time. So a growth model has a starting value of A, okay? A is our starting value. And then our growth rate is 1 plus our rate of growth. So if something grows by 9%, you would take 1 plus 9% as decimal, and we raise it to the t power. For decay, we take a starting value of A still, and then we take 100% basically minus our decay rate. So if something's going down by 9%, we're left with 91% of it after each year, okay? So I'm going to show that with a couple examples, but the thing here is A is the initial amount, R is the percent increase or decrease as a decimal, so 1 plus R should make sense that our value is bigger than 1, and then 1 minus R is decay because it's smaller than 1. So to give you a real-life situation, talks about the value of a car, very applicable. It says the value of a car in thousands of dollars can be approximated by the model y equals 25 times 0.85 to the t power, where t is the number of years since the car was new. So it says, tell whether this model represents exponential growth or exponential decay. And we know that this model represents decay. And part of it is the context of the problem. It's depreciation. We know cars decrease in value as they age generally. And the thing we want to be able to say is that has a factor, or it has a decay factor of 85%. So that means after each year you own a car, it is worth 85% of its value from last year. So the annual percent decrease, it's going to be a decrease. And what I'm asking for in part B is find the annual percent decrease. So that means I'm just going to really think of this as, if I'm left with 85% of something, how much percent, was lost? So I just would take 100% minus 85%. So it would be a 15% decrease. So the car decreases in value by 15% every year you own it. So it should make sense that the first year of a car is when it depreciates the most. So we want to estimate the value of the car, or when the value of the car will be $8,000. Now, I haven't shown you a lot of strategies for this yet, but essentially what this is us testing values, okay? So you can do this a few different ways. You could take this function and graph it in Desmos. That's what I would do. And I would find where the y value is 8,000, okay? But really, when we think about this, I should have been more specific. Really, I want to find when the y value is 8, because a y value of 8 corresponds to $8,000, because we talked about in the function, the value is in thousands of dollars. So the 25 really means $25,000. So if you wanted to go in Desmos, you would just click on the graph and look for a y value of 8, all right? So with this, if you do that and you go into the graph, it's not going to land on a perfect number, all right? But if you drag along your graph, it's about, when t is about 7 years, okay? A different way you could do it is you could plug in for 1 year, 2 years, 3 years, 4 years, and just keep going. But my suggestion here is to use Desmos and then find when y equals 8. It'll correspond to that $8,000. So with problems like this, more of it is you understanding that the value is y, the years is t. But when you graph this, just make sure instead of t, you use x as your variable, okay? So with writing a model, this is more the thing that's going to help us understand how growth and decay work. But it says, in the year 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. So we're going to write a model giving the population in billions after t years after 2000. So the first thing I'm going to do is I'm going to start with y equals. And what we've got to realize is that we always start with a starting value, okay? So our starting value is this 6.09 billion. That's the starting population. And to write our growth model, we take 1, and since this is growth, it's 1 plus our growth in percent, but as a decimal. So 1.18% as a decimal is 0.0118. And that is going to be to the t power after t years, okay? So if you wanted to write this as this is really, I'm gonna do this in a different color. This is really 1.0118. If you wanted to substitute that instead of the 1 plus 1.0118, sorry, you could do that. So if you want to figure out the population in 2005, this function is in years after 2000. So to evaluate this, I would take 6.09 times 1.0118, and I'll raise it to the 5th power because 2005 corresponds to 5 years. So if we go and we evaluate that for t being 5, what we would get, and I'm going to use a little bit of, approximation, but if I'm going to round to 2 decimal places, it's about 6.46 billion people. So I get out 6.46, but I know that's in billions. So the reason I plugged in 5 is because our function is for years after 2000. 2005 is 5 years after 2000, okay? And then estimating when the population was 7 billion, that's where you substitute our function into Desmos and then find when y is 7, okay? So what that would be, what would that correspond to? That would correspond to about 12. So it would be roughly in 2012 when we would have a population of 7 billion, okay? So if we're predicting, I know this information is a little outdated, but when we talk about this is how we model things, and we decide how the population growth is going in a city to see if we need to build more housing, if we need to build more stores to accommodate. So some of that stuff, we use modeling to predict short periods into the future. We use trends, and we use exponential models to figure out those trends. So for you guys, the most common thing is compound interest, and you are going to get more practice with compound interest than anything else because I think it's the most relevant thing. So compound interest means you deposit something into an account and it pays interest at an annual rate, okay? But that annual rate gets compounded sometimes more than once a year, okay? It can get compounded monthly, it can get compounded quarterly, it can get compounded daily. There are a lot of different ways interest can be compounded. Well, we're gonna talk about basically all those ways together, all right? Because I think that's a really effective thing to know how the different rates change, you know, and how much they really matter in terms of how much money you can actually earn. So you have an initial value, you call that the principal, okay? That's P, that's your starting value. And then you have a growth rate of 1 plus R over N. So R is your rate as a decimal. So it's gonna be a percent, okay? N is periods in a year. So if it's monthly, N is 12. If it's quarterly, N is 4. And then T is years. Okay, so you deposit $9,000 in an account, so that's P is 9,000, all right? It pays 1.46 annual interest, so that means R is really gonna be 0.0146. And then T is 3 because it's 3 years, and it is compounded quarterly. So that means the number of times it gets compounded in a year is 4, okay? So, before we do anything else, I'm just gonna highlight that T. We're gonna leave T alone for right now. We're gonna plug that in after we write our model, okay? So we're gonna leave T alone for right now. To write our model, the amount in our account starts with $9,000. We apply our growth rate, 1 plus 0.0146 over 4 to the 4t power. So that's just me substituting from this formula. So to evaluate this after 3 years, I'm going to plug in 3 to the model we just wrote. And you're going to have to do a little bit of calculator work, and I can help you with that. But this is a good thing, good tool to know how to use. So let's do the 4t power. 4 times 3 is 12. So I'm going to do this pretty quickly, but that's because I have this in front of me. I've already worked this problem out. But if you want to pause the video and work out and just think about where you get these numbers, you're going to get practice doing this. But if you want to pause the video to work out the 12 years, or the 3 years, you can do that. But I'm going to give you guys that the amount would be about $9,402, and I would round to 21 cents. So you're going to get practice writing functions for compound interest and evaluating them for different numbers of years. So this is a really effective skill to have, because then it helps you understand how car loans work and how not to get screwed on a loan, basically. So you're ready for practice. The practice is going to have some graphing, it's going to have some writing of models, and it's going to have some compound interest, which I really think is effective.